Welcome back to the gmShiny video tutorials. In this video, we are going to talk about the shape patterns page. So as before, we are working with the example plethodon data set that we loaded in the data input page. And we had some settings that we changed, but largely this should look the same regardless of whether you have followed this tutorial video by video. So you'll notice that in the shape patterns page, we have 4 different tabs here. They correspond to modularity, integration, symmetry, and phylogenetic signal. Starting with modularity, the first thing we see here is a plot of the mean shape of your data. And we have the links that were defined in the data prep page passed forward. And at the moment, some of these dots are colored in one color, while others are a different color. And I just increased this landmark size to demonstrate that we've got these looking red, these down here looking black, and that's just the default setting for when you first arrive to the modularity page. You can adjust which landmarks are associated with which module over in this setting panel over to the right. So first, choose the number of modules that you have. Let's say we have 3 modules in this data set. A third spot popped up to give us a room for another module. And now we can just drag and drop which landmarks we are testing in different modules. So let's say I want this back end of the head, so 10, 11, 1, and 2 to be one module. Then perhaps maybe this middle part of the head is going to be a separate module. So let's pull 3 down to the second module. So 3, 8, and 9. And then we'll just have 4, 5, 6, and 7, the very front of this plethodon head, be a different module. Now you'll notice as I was dragging and dropping, the colors didn't change to correspond to these changes. You have to finalize your module assignments and press this assign LMs to modules button in order to finalize the decision on your landmark assignments. So now we have this nice picture of one module to the right, one in the middle, and one over to the left. And the colors correspond to these options here that can just be adjusted easily. And the colors adjust without having to repress this button. But anytime you drag and drop a landmark, you'd have to reassign those landmarks to the modules. Now that we've got our modules assigned, we can scroll down to see the results part. Here, this first plot is the degree of modularity overall. We have this R output that you'd see if you were using geomorph in R directly, where we've got what was actually called, and we get our results, the CR, p-value, and effect size, and then a note on how many random permutations were used. On the left, this is the plot that's produced by this set of analyses, and this arrow here shows the observed CR value, the observed CR coefficient, and the gray bars represent the null distribution produced by that random permutations. So we can see here that this observed value of 1.1049 is nested very comfortably within the random permutation distribution, which corresponds to a fairly high p-value. So we would not expect, we would not conclude that modularity exists in this data set here. A setting over to the right would change this modularity test to something that's phylogenetically informed. And this is an option only if you, again, upload a phylogeny with your data. And so if we change this option to evaluate modularity in a phylogenetic context, the thing that's changed here is what was called. It's a different function in geomorph, but the results are largely the same interpretation-wise. We get a CR coefficient, we get a p-value, an effect size, and then again, the plot is as it was before. Down at the very bottom, we've got another test relating to modularity where we are testing whether evolutionary rate varies between the modules. Here we have a rate ratio that's produced and then a p-value based on that rate ratio. Same interpretation of the plot holds, however, with this arrow indicating the observed rate ratio and the distribution indicating what was generated by the random permutations. Here, we also get rates for each of those groups on their own. Moving on to the next tab here, we're going to check out some options with integration. Right away, we see a plot that is indicating the global integration in these data, and we can scroll down to see some more interesting things that tie in with the previous tab, the modularity tab. And this test here is calling the function integration test, and here we are testing whether there was integration between the modules that were defined on the modularity tab. So if this is an interesting part of the integration page for you, make sure that you visit the modularity page first. You'll notice here that for our particular data, I defined 3 separate modules, which means that there's not a plot available for this particular test, but nonetheless, we still get some results over to the right. We get the result, the RPLS, we get the effect size, p-value as well. Then we get some pairwise statistics, pairwise effect sizes, and pairwise p-values. So lots to look at over here. We can also have some different things be tested with this integration group. In particular, we can test the integration groups as defined by any discrete trait that you have uploaded. Once you press that, it'll give you an option to specify which level of the data you want to use. And so for our discrete example, data B, we only have 2 levels, and the options are A and B. Again, this is a little bit arbitrary with the modules defined as they are because the plot doesn't show up. But if we were to go back, let's go back and turn this back into just a data set with 2 modules, assign that to the modules, move forward, come back to this page here, we get a plot, and we can plot these based on the trait level of discrete example data B. The third tab in here is the symmetry tab. This is quite complicated and requires a different data set. The example plethodon data set are not symmetrical by nature, and so they can't be a good use of examples in this data, but I'll provide another clip at the end of this video that uploads example data that are appropriate for symmetry, both object and matching symmetry. The last tab on this page is about phylogenetic signal. This is a very simple tab where we're just producing the results from the function phi signal, and we get an observed K, a p-value, effect size, very similar to the previous results we've seen. And similarly, the plot on the left can be interpreted with this vertical arrow being the observed value and the gray distribution as the random permutations. On the right, we have an option to test the signal of the shape that we've uploaded, but we also can test other variables that are continuous that you've uploaded. So we can look at the phylogenetic signal of the continuous data that we uploaded, or we can look at the signal of the centroid size. As I mentioned in a previous video, the centroid size was generated in the act of running the generalized Procrustes alignment, and that was passed forward. So if you are uploading shape data that were previously aligned and you indicated that in the data input page, you would have to upload independent centroid size data in the trait column in order to use this. But since that's not the case with our example data, it's passed forward naturally. Here we are back at the data input page, and I'm going to upload some example data sets that are good for demonstrating the use of the symmetry tab on the shape patterns page. These example data sets can be found on the GitHub repository in the folder called testing datasets. We'll start with this one. It's in the symmetry tab. We'll start with a lizard example. So I am going to upload our lizard symmetry data set. We will choose to run this GPA and jump over to the shape patterns page and the symmetry tab. This data set can be found in the geomorph package, and it is a good way to demonstrate object symmetry. That's when you have a lot of shape specimens where there's symmetry within each of those different specimens. So if you look at this as a lizard head from the dorsal view, the nose is tipped over here and the body extends out to the left. And in the symmetry tab, you can use this part of the main panel to visualize what you're defining in terms of symmetry. So the first thing to look at in the settings panel is the symmetry type. With this example set, we are using, this is representative of object symmetry. So in this case, you need to do a handful of things. You need to define the specimens based on their identity as an individual and as a replicate. That is to say, do you have several specimens that represent the same actual individual lizard in this case? For the purposes of this video, let's just say there are no replicates. So you press that button and it says the user indicated that there are no replicates in the data. If there are, you can press manual entry or upload a file. Let's take a look what this looks like. A manual entry would just mean these are the specimen names and you would identify each of their individual or rep assignment. But again, let's say that there are no replicates. Next, we have to assign landmarks to the sides, and this is true only for this object symmetry type. In this case, we have a CSV that tells us which landmarks are associated with which file. So I'm going to upload that. This is this particular CSV, liz.lm's side. And right here, you can see what that CSV looks like. It's got two columns, one for each side of the specimen, and the landmark numbers are paired with respect to the landmarks they are mirroring. So you can see landmark 13 is a mirror of landmark 14. And over on this image, you can see 13 is paired with 14 by color. And this visualization here is just to make sure that things uploaded or were manually entered the way that you would like them to. The way that this has changed in terms of visualization is all of the unaffected landmarks stay as black circles, whereas all of the landmarks indicated to be the same side on one side are the same shape. So in this case, square on the top and then triangle on the bottom. And the colors indicate which pairing is represented in this file. So just take a look at this visualization to make sure that it has been produced the way you wanted it to be produced. Once that looks like the right assignment for symmetry, you can press this calculate button. And that'll run some analyses that will show up in this symmetry of shape variation box. Lots of things come out. All of this is what would be produced if you were running this bilat symmetry function in R. Here we've got the shape ANOVA, where you've got, you can look at your z-scores for the individual, the side, the individual by side, etc., and the p-values associated with that run. And you're also given the output values of individual signed asymmetry indices, as well as individual unsigned asymmetry indices. These can be, this is a fairly large amount of data, and you can export that as a CSV table. You can also export this plot over here that shows the directional and fluctuating asymmetry over here. Importantly as well, we can use the symmetric or the asymmetric components of shape variation in the other parts of the app. So if we would want to push forward the symmetric component of shape variation, we could press this button right here that says use symmetric component of shape variation. And that would replace all of the shape data with the symmetric component of shape variation. And that can then be used in the Morphospace Warp Grids page, as well as the linear models page. Same thing is true for the asymmetric component of shape variation. This button here would use the asymmetric component of shape variation pushed forward throughout the app.